Now, in an atom, electrons can be excited. That means that a photon can be absorbed by an electron in an atom, and that electron can actually escape or jump up to a higher energy level. It stays there for some time, usually a very brief time, 10 to the minus 8 seconds or so, before falling back down, either releasing the same energy photon, or it can cascade down, each step downward releasing a different amount of energy, appropriate to whatever the energy transition is for the jump it makes. So for example, a photon, the lowest energy n equals 1 level, can jump to n equals 10 by absorbing a very energetic photon, and then it can cascade down to n equals 7, n equals 3, and then n equals 1, giving off a photon with each transition. So that excitation and de-excitation, we can talk about some interesting properties that occur because of the excitation and de-excitation of atoms. One obvious one is color, object color. For example, I'm wearing a green sweatshirt, or you see the different colors of ink on the dry erase board on this video. Black, blue, red, green, and purple. The reason these different colors exist is because the ink used, or the dye used in clothing, absorbs wavelength at some frequencies or wavelengths, colors, and not others. A wonderful example of that is leaves, right? Trees' leaves are green because of a pigment called chlorophyll in the leaves. Now chlorophyll, actually, here's a spectrum, absorption spectrum for chlorophyll. Chlorophyll absorbs blue light, it absorbs red light, but it doesn't absorb much green light. So it reflects that green light, allowing us to see leaves as being green. My sweatshirt, again, the same property. It's not absorbing the green, which is why the green is what's reflected back off of it towards your eyes, and you see this sweatshirt as green. When chlorophyll leaves a leaf, then the leaf no longer absorbs a lot of yellow reddish light, and that's why you see the leaves turn colors. So object color deals with atoms or molecules that preferentially absorb some color and not others. And you might have experienced this sun bleaching, right? If you've ever seen an old advertisement made on just a generic printer that's been sitting outside on a post board somewhere, you can see that the colors fade. Or if you leave a business card on your dashboard of your car, the colors begin to fade. That's because the sunlight, the energetic photons in sunlight, break up the dyes that absorb certain colors. So if you ever get an outside sign professionally printed, like a big banner that you want hanging out in the sun for months, you need to use inks that can withstand the ultraviolet radiation coming from the sun that can break up these dyes. So you have to basically create UV-proof inks to prevent this sun bleaching that can occur as the sun's rays break up pigments and dyes in colors in objects. Now, another thing you've probably noticed, fluorescence. Many of you now in your homes, you might have what are called compact fluorescent lights. They're the little corkscrew light bulbs, you can see one over here, that are replacing the incandescent bulbs, which are energy hogs. Now, fluorescence is a property where an atom or a molecule will absorb a high energy photon, usually ultraviolet photon, but will emit an optical one. So, or many optical ones. So in the fluorescent lighting you have in your home, or in the fluorescent lighting in the classroom over my head, there's a high energy discharge tube, those long glass tubes that you see in stores, those fluorescent tubes. There's a rarefied gas in there that, when placed under a high voltage, gives off ultraviolet light. So if that was just what the tube was, this room would be black. It would just be nothing but ultraviolet light coming down, and that's damaging to your eyes, can cause sunburn and so on. That's what you see actually in sunbeds, ultraviolet light in those fluorescent tubes. But we don't want to get a tan here in the classroom, and some of us can't tan. So what we do is we coat the inside of that fluorescent tube with fluorescent materials that absorb the ultraviolet light given off and then emit optical light. Now we try to have it emit optical light over the whole wavelength of rainbow, but I'll show you here to the right, here's fluorescent lighting compared to an incandescent bulb. You can see that fluorescent lighting can miss colors or have strong blues and not very strong reds or so on. So what can happen is an object will look slightly different under a fluorescent bulb than an incandescent bulb. Now, the next thing your book talks about is phosphorescence. Phosphorescence is when a material or dye absorbs light but hangs on to it because it excites an electron to a high energy state. As that electron falls down, it falls into a state that's called a metastable state. A metastable state is just a state where the electron hangs out for a very long time before falling once again. Normally, electrons, if you excite them, like in the fluorescence, you excite electron with a UV, it almost immediately falls back down and creates an optical photon in several tens to hundreds of nanoseconds, so 10 to the minus 8 seconds approximately. For phosphorescent materials, that electron doesn't immediately jump down. It stays in that metastable orbit for seconds, minutes, or even hours. So billions of times longer or a bit more than it normally would in a regular non-metastable state. So what ends up happening is, if you take, like for example, a glow-in-the-dark sticker and shine light on it, when you turn off the light, that sticker still gives off light minutes or even hours after it's received light. It's re-emitting the light, the energy it absorbed, but it's doing it very slowly. So that's phosphorescent. And your book then moves on to talking about lasers. Now, lasers are a means of creating coherent light. So in a laser, what happens is you create a population inversion, which means that you have more electrons in a high energy state than a low energy state. Normally, if you have millions and millions and millions of atoms, almost all of them are in the low energy state, and very few are in a high energy state. And again, once they're in a high energy state, they quickly fall back down 10 to the minus 8 seconds or so, your book talks about. So not many electrons. As soon as an electron is excited, it jumps back down and gives off a photon. Or if it's excited to a higher energy state, it can fall down to give off 2 photons, but that happens very quickly. And you almost always have the lowest energy state being more populated than the high one. In a laser, you create a situation where the upper energy state has more electrons in it than a low energy state. It's called a population inversion. What happens here, electrons spontaneously decay. They will, given some period of time, randomly jump back down and give off a photon. But in a situation where you have a population inversion, you can create what's called a stimulated emission. And that's what laser stands for. Light amplification by stimulated emissions of radiation. So, a photon of the right wavelength comes by, causing an electron to fall down, giving you 2 photons that are identical, or nearly identical. Those photons pass through, causing 2 more electrons to fall down, and now you have 4 photons that pass through that are nearly identical, and that continues. And what happens is usually a mirror is placed on either side, so the light bounces back and forth a lot. One of the mirrors is slightly transparent, giving you a laser. So if you've ever used a laser pointer, that's basically what you're doing. You press the button, the voltage sends basically light, stimulated light through, creates a population inversion, sends light through repeatedly, giving you a beam of light that goes in the same direction with the same energy, the same frequency, the same momentum. Now, lasers are incredibly useful in modern society, right? Blu-ray discs and DVD players and CDs all use lasers to read. The game systems you might be familiar with the exception of, the Wii U does it. The new Switch, I don't think uses discs, but the Xbox does, the PlayStation does, and most of the game systems do. The lasers for industry, if you've ever seen an image of, here I'll show a quick image, of a laser basically removing rust off of a piece of metal. You can actually blast the laser in very brief high energy bursts. It'll actually burn off and clean rusted metal. You can use also lasers for engraving. You can use lasers for surgery. LASIK for correcting eye surgery uses an ultraviolet laser to actually cut the lens of your eye in order it to reform to fix your vision. So lasers are incredibly useful. The laser didn't really exist. There's some lasers that exist. They're called masers. They're usually microwave light in space. But the lasers that we know of didn't exist until after Einstein. Einstein actually did the math to show that lasers can actually exist. So Einstein basically helped discover lasers, which is amazing. And then finally, the idea of a hologram. A hologram is a three-dimensional image trapped in some medium. And by 3D, I mean that when you look at a hologram, if you move your head, the things inside the image actually move. So you can see behind objects in a hologram. Holograms are, if you've ever seen a real hologram, they're amazing. It looks like you're looking at an image. Usually it's done with lasers, so everything's in one color. But you can actually move your head around. If you have a little magnifying glass, you can see what's magnified, it's changed. It's very impressive technology. Now, ideally, and of course in sci-fi, you see like full-size, life-size holograms of people. We don't have that technology yet, sadly. Hopefully we'll get there at some point in the future. But right now, holograms are basically light that is, lasers are used to trap a pattern in a medium. So when you shine light on that material, it gives you back the light that you used to create it, or similar light, the same pattern that you used to create it, giving you that hologram appearance. So you've probably seen like the really inexpensive holograms. You might have them on your credit card or debit card, a little eagle or something like that. Holograms are very interesting objects, but exist because of lasers, which exist because of an understanding of how atoms work, excitations and de-excitations of atoms.